Okay, section 2.3, first of two videos. Okay, we're back to talking about sets. And we're going to look at two big properties at first. First is the intersection. So we have two sets, C and S, and we want to mail a questionnaire who are college graduates and who earn at least $40,000. So the questionnaire is going to the individuals that are in both sets. That's the intersection. That's where they overlap. So people that are in here are both a college graduate and earn at least $40,000. Here's our symbol for intersection. Notice the key word, as it's pointed out here, is and this is a lot like P and Q. This is the conjunction. Notice that the and in our logic looks a lot like the symbol for intersection. Okay, let's do a couple of quick examples. So I want the intersection of A and B. I want the elements that are in both. Looks to me like 3 and 4 are in both. So the intersection of A and B is 3, 4. With the second example, these are all even. B is all odd, so there are no elements common to both. So the intersection is the null set. And we say that these two sets are disjoint. They do not overlap. A quick diagram would look like this. There's A and B. So the intersection is the null set since they share no common elements. Okay, union. Want to mail a questionnaire to the individuals who are college graduates or who earn at least $40,000 or both. Now this could be anyone in either set or even in the intersection. So union looks like an upside down U. This is the same as P or Q. This is the disjunction. And the key word is or. So intersection and unions are very important. So let's do examples of union. Okay, I want to put A union B. So it's all the elements in A. There's 1, 2, 3, 4, and all the elements in B. But notice 3 and 4 are already included in here, so we don't need them again. So I just add the 5 and the 6. In the second part, okay, B looks to be like the natural numbers, 1, 2, 3, 4, and so on. A looks to be the even numbers. Well, here A is actually a proper subset of B. That looks like this in a Venn diagram. There's B. A lives in between or inside. So if we shade the union, looks to me like we just get B. So A union B here is just the set B. Okay, set difference. It's kind of a strange thing. So I want the set of individuals earning at least $40,000, but not a college graduate. Let's see. I'm actually going to draw the Venn diagram. Let me do some colors. Let's do C. Those are the college grads. Let's do S. Those are the ones who earn at least $40,000. Excuse me. So I want the set of individuals earning at least 40,000, but not a college graduate. So that's everyone in here. They're making 40,000, but not a college graduate. So it looks like there's a bite taken out of set S because the people in here in the intersection are college graduates. So this is the complement of C. Remember, complement means everything not in C relative to S, because it's the stuff in S that's inside the complement of C. You may also see this as the set difference of S and C. Now, here's the note I was going to read. I'll do it here. This is not B minus A. It's the set of all elements in B that are not in A. I just call it the set difference between B and A. This is a good exercise for you to do to show these are the same thing. But notice the set difference or the relative complement of A relative to B. I always get that mixed up. Complement of A relative to B. There. Meaning stuff not in A that's in B and only B. Not the stuff that's out here, because that's also part of the complement of A. All the other stuff in the universal set. Okay. Well, let's find the set difference between A and B. Well, here's A, is D, E, F. Is there anything in A that's not in B? No, because A is a subset of B, so this is the null set. Now, if I say the set difference from B and A, now I can see that there's 3 elements in A that are in B. I don't want those because those are in the intersection. So I have A, B, C. Okay, same thing here if we do the set difference between B and C. Notice that again, C is a subset of B. So this is also, we're just taking out the intersection part of A, B, and C. So we get D, E, F. And then if we look at the set difference between C and B, again, this is the null set. I know you may not know this word yet because we haven't done it with numbers, but just means that the order doesn't matter. And you can think of addition, 3 plus 2 equals 2 plus 3. That's what commutative means. So notice that intersection and union have the commutative property. Associative property. I'll do it with addition again. 5 plus 6 plus 8. You know, we say do parentheses first. Well, it doesn't matter how we group these. That's the associative property. I can move the parentheses. So intersection and union also have the associative property. Now, here's where I actually want to prove something, the distributive property. I'm going to do this. I need two Venn diagrams. I'm going to do the Venn diagram for the one on the left and then the one on the right. Show you how to shade these so that we can prove conjectures like this. Okay, I'm going to do this. Now, when we do 3 sets like this, we always set them up A, B, and C. Notice we have intersection all over the place. So let's do inside the parentheses. Let's shade B union C. And let's do that with green. So B union C is everything in C, everything in B, or both. We get the intersection there. Now, where does A intersect this? Let's do A in purple. Notice how I'm doing this horizontally. I'm shading in A. And now, where is the intersection with all of this? It's where the crosshatched is. So if I can just outline that with red, here's where we're looking for. This is A intersect B union C. Now, let's do another one for the right-hand side and see if we get the same thing. Let's go with blue again to this big A, B, C. Okay, we're doing what's inside the parentheses first. So let's do A intersect B in green. Okay, here's A intersect B. And now let's do A intersect C, purple. Here's A intersect C. And I want the union, so I want everything that's in there. So if I just quickly outline this in purple, notice that's the same thing as up here. So that conjecture is true, and it's like the distributive property of the intersection is being distributed over the union. And that's the end of this video, because this looks like a fun problem to start another video.